Hi there, it's Chem Coach Powers, and it's time to cover 16.1b. Today we're still covering Chapter 16.1, but we're going a little bit more in depth. We're going to be talking about enthalpy. Our objectives here today are to distinguish between endo and exothermic processes, to define enthalpy, describe it in terms of its energy change with regard to a sign, like the sign convention, like it's positive or negative enthalpy. What does that mean? And then to calculate the changes in enthalpy for given amounts of reactants and products. The criteria for success given process, you will be able to state by the time we're done whether the process is endothermic or exothermic, and explain why with regard to the energy that's in the bonds, for instance. You'll be able to describe the relationship between energy and enthalpy. They're not the same. And you'll be able to explain what the sign of an enthalpy change means about the process. We just talked about that. And if I give you the mass of a reactant or a product, you're going to be able to incorporate the old school stoichiometry that you learned a long time ago with the new thermochemical equation that we're going to show you today, right? That'll give you an associated enthalpy change. So your enthalpy of reaction. The enthalpy is defined as the energy that's absorbed or released as heat during a chemical reaction at constant pressure. Now remember, these are chemical reactions, and in chemical reactions you can have changes in the quantity of gas which can change the pressure. So we need to make sure that we talk about the fact that the pressure is not changing, because remember that pressure can also affect temperature. We learned that from the gas laws, right? So constant pressure is important here. Now the symbol is delta H, and you notice we have the little RXN here. That just stands for reaction. So this is the enthalpy of the reaction. Remember that enthalpy is defined as a change, and so when we see the delta, that means change, right? So this is delta H, and it's the change in enthalpy that we're going to be talking about here today. So how do we define enthalpy in terms of a formula? Well, the delta H is equal to the heat energy, in a sense, of the products minus the heat energy of the reactants, okay? We want to see what the change in total amount of energy is, and this is going to be something we'd measure in a bomb calorimeter, for instance. We'd see how much energy is given off or how much energy is absorbed when a reaction takes place. So that sign here is important to pay attention to, because basically this sign means that if the reactants overall have more potential energy stored in them than the products do, then the enthalpy is going to be negative, okay? Because that's going to be a negative because of that sign. You can have more energy in the reactants than the products. That means your overall enthalpy is negative, which means this is an exothermic reaction, okay? So exothermic processes are ones in which the reactants have overall more energy, potential energy stored in them than the products do, okay? So as you get to more stable states of compounds where you lower your potential energy, typically those things are going to be exothermic processes, right? So think about burning reactions. That's going to be exothermic. That's going to be a negative delta H. That's going to have negative enthalpy signs. So it's going to be yeah, I just said that. I don't need to say it again. I do want to point out that this is definitely dependent upon the amounts of the reactants and products. If I had 1,000 grams of something reacting compared to 10 grams of something, the 1,000 grams of that same substance is going to end up having a total more energy change than the 10 grams, right? 10 grams is not going to have as much energy change as 1,000 grams, just because of the idea of more chemical means more energy, right? So that's the idea there. Now let's look at an example of it, okay? So if I wrote this problem here, and notice I've got a little plus sign right here. That plus sign means that I'm adding energy, right? So if I look at it, it says, hey, I'm starting with hydrogen gas, and this is going to be a simple reaction that you kind of know, right? Hydrogen gas is burning in the presence of air. If I take some hydrogen gas in a balloon, put a little lighter next to it, and it blows up, fire, right? What does it make? It makes water. But not only does it make water, it makes another product. The other product it makes is energy, right? So it makes 483.6 kilojoules of energy if I have a certain amount of it. What does that mean? Well, that means my delta H, my overall change in enthalpy, is negative 483.6. I've given off 483.6 kilojoules. I've gone from a place where I had more stable state to less stable state. Try that again. less stable state to more stable state. So let's look at my reactants. My reactants are hydrogen, right? So we've got a couple little hydrogen molecules up here, sorry, and then an oxygen molecule. And those are my reactants. And if I burn them in the presence of some starting energy, I'm going to form water. Now, what does this all mean? Well, this means that I've got to take some initial energy.
You are dismissed. Thank you again. Have a wonderful spring break, and we'll see you in a couple weeks.
This means that I've got to take an initial amount of energy that I put into it, and that initial energy starts to break these bonds up, right? And then when I'm done, the new thing that forms, some of that energy is going to be put back into forming these bonds, all right? So it's going to store some of that energy in the bonds, but I'm going to have extra energy left over. So some of that energy that was stored up in here, it came out, and it's now going into the environment. It just goes into the system. And so that's what this 483.6 kilojoules is. My reactants are going to be higher potential energy than my product. So I've gone from a higher potential energy, drop down to a lower potential energy. And so now I'm going to have this excess amount of energy here given off in the form of heat. Okay, does that make sense? All right, so let's look at the exact reverse of this reaction. Let's look at an endothermic process, right? In an endothermic process, we would have the plus sign over here on the reactants side. Okay, so this is on the reactant side now. It says it's taking 483.6 kilojoules of energy added to water in order to make this happen. Well, you guys have seen this process before. Okay, you've seen this reaction. You guys might remember electrolysis, right? If I take some water and I electrocute it, bzz, there's my little lightning strike. Bzz, okay, I'm electrocuting my water. What's happening is I'm going to break some of those bonds, and then the little hydrogens are going to go over and they're going to go to the negative electrode, and they're going to take a little bit of extra energy and they're going to form hydrogen gas. And my oxygens, they're going to go over here to my positive electrode, and they're going to form oxygen gas, new molecules. Well, it took some energy to do that. In fact, it took a little extra energy to make these new molecules than the water had in the beginning. And so it had to absorb extra energy. It didn't have enough energy from the bonds itself. It had to absorb extra energy from the environment, from the electrolysis, the electricity, things like that, right? So it's going to now form some new chemicals, but those are going to be less stable. And so it starts down here, takes extra energy to form into that new product, right? So these are going to be my reactants with lower potential energy. And those are my products up there with higher potential energy. And so this is a positive enthalpy. 483.6 kilojoules is what's being represented here. Okay, so positive delta H means it's endothermic, meaning absorbing its energy, right? And the energy of the products is greater than the energy of the reactants. And when I say the energy of the products, I'm usually referring to the potential energy, right? That's kind of a way that we can talk about that. The energy that's stored in the bonds is greater in the products than it is in the reactants. Okay, so this is another way to look at it graphically. If you kind of pay attention to energy over here and energy over here, right? If I'm going from high potential energy stored up here, and then I make something that's lower potential energy, a little bit more stable, then it's going to give off that amount of energy, and it's going to be exothermic. If I'm going over here and I'm dealing with mercury, all right, so my mercury oxide has low potential energy, and I got to put some extra energy into it and store energy in these bonds of mercury and oxygen, then it's going to be requiring to absorb energy. And so if my delta H is greater than 0, it's a positive value. All right, that means my products have a greater amount of potential energy than my reactants, right? And so this is going to be a positive value. That's going to be endothermic. And exothermic ones are going to have delta H's that are negative 0 or less than 0, which is negative, right? And so my energy of my products, is actually going to be less than my energy. I'm sorry, my products. Here you are. How about that? Products and reactants. My energy of my products is going to be less than that of my reactants. As long as I draw the right place, it makes sense. So I would say to take a look at this graph. This graph is probably going to be a good one for a test. And you kind of saw me do a similar version on a previous slide. But as the energy, here's your energy, right? The H, and here's the time that's going by to have the reaction take place. Endothermic reactions are going to look like products up here, reactants down here. Exothermic reactions are going to look like reactants up there and products down there. Okay, so know that graph for the test. That would be a good one to know for the test. All right, so now I'm going to have you guys contemplate and answer some of these questions and see how you do. All right, so just to verify that in writing here, we had exothermic, endothermic, endothermic, and exothermic. Okay. All right, so let's look at what a thermochemical equation would look like. So we're seeing a chemical equation now, but now we're putting some energy into it. So you'll notice that it says that the thermochemical equation is going to have the heat, all right? The energy released or absorbed as heat is written. So we want it written, and it can be here externally where we have the delta H written outside of it, or it can be inserted in with a little plus and minus signs to the reactants or the product sides, right? So either way, we can talk about them as thermochemical equations. Typically, if we say write a thermochemical equation, we want you to actually write it into the actual formula. If not, we'd say write the chemical equation and its enthalpy change or something like that. So what we have here, that's all part of thermochemistry, but what we have written here is chemical equations with their enthalpy changes. And so you can see that the reverse reaction that we have here, right? So this one has got the H2 and the O2 on this side, but this one has H2O. Remember that these signs are exactly opposite of each other, okay? That's important to pay attention to. And the other thing we talked about already that they had to do with amounts, right? All this stuff has to do with amounts, but we didn't really talk about what that means yet in terms of the energy. Look how I have, I'm going to go to this one here. I have 2 H2 and 1 O2, right? Gives me 2 H2O, and that gives me this value here, negative 483.6. Look what happens when I double everything. I have 4H2 plus 2H2, or sorry, plus 2O2 gives me 4H2O, and I doubled my enthalpy. So when I write this value here and I talk about the number of kilojoules it's giving out, I have to pay attention to my coefficients because that value in kilojoules is corresponding to a value for my coefficients that I have in my balanced chemical reaction. And so if I'm increasing by a factor of n in terms of the number of moles, right, then I'm increasing my enthalpy by an equal factor. I have to multiply by that same factor, okay? So the coefficients are corresponding to moles. Pay attention to that. The coefficients are corresponding to the moles. And so when I give a kilojoule value, that kilojoule value is based upon a mole value that I have written in my chemical equation. Okay? All right, so finally get to the question that was posted a little bit earlier. We include the physical states because the energy changes are different with different states. So think about if I am changing from water, solid water at 0 degrees Celsius, to liquid water at 0 degrees Celsius. Notice that there's no change in temperature. I haven't heated the water up in terms of degrees of Celsius at all, but it still took some energy to do that, to go from solid to liquid, to break those bonds. Remember that the solid is going to have these little hexagons that it forms, right? Solid water forms these little hexagons. To break those bonds and free up the water to kind of just move around freely, that took energy. How much energy? 6.01 joules. But look at this. If I have 100 degree Celsius liquid water and 100 degree Celsius gaseous water, that takes 44 kilojoules. So now my little water molecules are, floating around and they're moving around each other, right? But if I want to energize them enough to escape the surface of my liquid, right, and get them to evaporate or to boil, right? It's not really evaporating at this point. I'm actually vaporizing them, trying to get them to turn into the gaseous state. That actually takes a whole lot more energy, 44 kilojoules. So we have to talk about the states of matter because if we are changing states, then that actually can be incorporated into our equation as well. It needs to be incorporated into our equation. I'm never going to give you a chemical equation that's going to change states that you have to worry about that for the test, but you should just be aware that that is why we are putting those states of matter on there. It makes a difference. All right, so we have a question. For recording thermochemical equations for reactions, should we write the delta H assuming the coefficients are representing moles, or should we write the delta as kilojoules per mole? Yeah, so we won't, we're not going to write kilojoules per mole most of the time. We're just going to do kilojoules, and then we look at that equation. Actually, I'm going to show it to you on the next one here as this example, and you'll see why we're just going to do kilojoules in this example here. That's a good question. All right, so let's look at this. I've got some white phosphorus, all right? So this is elemental white phosphorus, P4. It's a solid, and I've got 266 grams of this stuff. I'm burning it in air, and so the air part that it's reacting with is the oxygen. It's going to take 5 moles of oxygen to react with 1 mole of the white phosphorus to give me 1 mole of tetraphosphorus digoxide. That process gives me negative 3,013 kilojoules. Now, think about whether that's exothermic or endothermic for me for just a second. Okay. And if you're thinking about the answer there, you should be thinking exothermic. Remember that negative value right there means that it's exothermic. Excuse me. So how would we do a problem with this? Notice that I use the word up here, stoichiometry. It's one of our favorite words, right? Nice, fun word, stoichiometry, that I'm incorporating some of the stuff I've learned before into some new concepts now. So now I have this value of kilojoules. What does that mean? Well, if I look at 266 grams of this white phosphorus, and I think about my molar mass, remember, I got this value from the periodic table. I took phosphorus's molar mass and I multiplied it by 4. And now I can say that I've got 3,013 kilojoules. Notice that it's still a negative sign there for every mole of P4. But what if I'd asked the same question for oxygen, right? What if I'd said instead that this was 266 grams of O2 reacting with phosphorus? Well, what would that look like? Well, I'd have to do this. Now, this value is going to be different, right? For 32 grams of O2. And then this value is going to be different because I still have 3,013 kilojoules, negative 3,013 kilojoules. But what am I dividing it by now? By, this guy's head is in my way, by 5 moles of O2. Okay, so instead of 1 mole, remember that's a 1 right there. Instead of 1 mole, it's going to be 5 moles. So these moles are going to be able to cancel out, right? And so I'll be able to tell you the total amount of energy. But I can't just say kilojoules per mole because it could be a 5, it could be a 1, it could be a 1. Like, it's not just 1 mole each time. It's based upon how much of that reactant I have. And so we don't do the kilojoules per mole as we're writing that out, you know, as a delta H. We just say how many kilojoules there are for that particular equation with that particular setup of its particular balance coefficients. Great question. So anyway, our answer for that top one would be minus 6,470 kilojoules would be the total amount of heat evolved or given off as this white phosphorus burns in air. Great. Any other questions that we have? Okay. So let's see if you can do it. Okay, so now you're going to practice this and see what you can come up with. Your equation is how much heat is released when 4.50 grams of methane is burned in air. Your equation, which I'm sure you probably could have come up with, right, because it's a combustion reaction, but it's CH4 plus 2O2 gives you CO2 plus 2H2O. Notice that we've given you the delta H. When we do these problems, you'll either be given the delta H in the problem, or you can look it up in the back of the text. Okay, and we're going to show you a little bit about how to look it up in the back of the text in the next section. But you'll be given this value here that you can use. Okay, so I'm going to give you a minute to see if you can solve this problem, and then we'll see how you did. All right, let's see how you did here. So we got to start with our given 4.50 grams of methane, and then we look up our molar mass on the periodic table, 16 grams of methane. Should have a little bit more written in there, right? For every 1 mole of methane. And then we have the value of 1 mole, right, of our methane there. And so we can say negative 890 kilojoules for every 1 mole of methane. And that gives us 250 kilojoules overall that is given off. And so again, that negative sign means that this is exothermic, which is what we'd expect when we're burning something, right? So we'd have heat given off when we're burning methane. Okay. Any questions on that? So just got to be careful as you're doing these questions, because the enthalpy pirate is out there and he'll steal your joules. And that's not good. Sorry, a little humor. All right, so our objectives. Let's see if we can do what we set out to do. Can we now distinguish between endothermic and exothermic processes? Yeah, we've identified a few of those, right? We know enthalpy has to do with heat. It's about the overall amount of heat energy given off or absorbed in a reaction. And we know that a negative sign for delta H means that there's going to be an exothermic reaction. A positive sign is an endothermic. We can calculate changes in enthalpy for given amounts of reactants and products. We just did that. We used stoichiometry to do that, right? So you are now successful because I give you a process. You can state whether it's endothermic or exothermic, and you can explain why, talking about the energy changes, the bonds that are absorbing energy or giving off energy, right? Potential and kinetic energy. You can describe the relationship between energy and enthalpy. And remember that they're not the same, right? Energy is not the same as enthalpy, but enthalpy is describing a change in the heat energy present in the system. You can explain the sign of enthalpy changes. Yep, we talked about that already. You can, given a mass of a reactant or product, use and a thermochemical equation, use stoichiometry to calculate the associated enthalpy change. All right, so you're amazing. You can do all that stuff now. So thank you for going on that journey with me today, learning about enthalpy.